Hyperion is a parametric test shell for on-wafer electrical testing of semiconductor devices and process test structures. Parametric testing occurs in several functional roles of semiconductor manufacturing. These include the following: semiconductor research, which asks what are the laws of physics and chemistry of a new material or technology. Technology development, which asks how can a new process node be manufactured, or how can an old process node be migrated to a newer one. Manufacturing process control, which asks how well controlled is the manufacturing process and what direction should it be nudged. Device modeling for simulation, which creates mathematical models and parameters for simulation tools used in semiconductor design. Device and process reliability, which asks how long will a product perform as designed and manufactured in the customer's hands. Failure analysis, which asks can a product failure in the customer's hands be attributed to a design or manufacturing defect. Hyperion is organized into several areas. On the left is the wafer definition setup that works with the wafer prober to put the wafer at a commonly agreed location for testing to begin. In the center, reticle locations across the wafer can be selected for testing. On the right, each reticle location can have modules, devices, and test algorithms defined. But let's look at the physical reality of Hyperion's on-wafer interaction to make this more clear. On-wafer parametric testing uses specially constructed test structures defined across the wafer. These test structures are contacted by conductive needles of the probe card, which contact arrays of bond pads called modules. Modules consist of a variety of test devices tailored to the particular role requiring test. Devices within the module can have varying numbers of terminals. Some bond pads may be shared among multiple devices. Each device can have a series of test algorithms assigned to it. Once a module's testing is completed, the wafer prober is instructed to move to the next module in the test plan. Once all modules in a reticle are tested, the prober is told to move to the next reticle, and module's testing is repeated again. Chroma supports a broad range of parametric measurement hardware, ranging from classic GPIB instruments to our Chroma 3530 parametric test system. All algorithms operate on all platforms, with only differences being defined by the original manufacturer's test specifications. Cross-vendor and cross-equipment operation is possible with the same code and test plans. Hyperion supports a broad range of commonly used wafer probers, from fully automatic production probers to laboratory semi-automatic and manual probers. Hyperion offers libraries of pre-written, pre-validated test algorithms, typically used in industry. These libraries allow customers to get to testing and creating test data quickly. The Parametric library has most common algorithms used to characterize MOSFETs and BJTs. The Reliability library has most common algorithms used to characterize dielectric, metal line, and MOSFET reliability. Hyperion offers an algorithm development kit based on Microsoft Visual Studio C++. Customers can port or create their own algorithms. The Algorithm API manages vector test results automatically, in addition to the typical scalar results. Algorithm plots provide valuable feedback to know testing is proceeding as expected. This includes algorithm plots, which allow automatic runtime generation of vector data plots. Certain algorithms have customary plots associated with the data measured. Algorithm plots allow these customary plots to be encoded into the algorithm. Test result output formats define how test results are generated and stored on the computer. A number of standard formats are provided, such as comma-separated value and Excel. Many customers have unique requirements, which can be customized using our output format plugin system. Test plans from legacy systems and central IT test plan systems can be imported with the Test Plan Import Framework using customization by Chroma Application Consulting. Hyperion provides a powerful yet easy-to-use parametric test shell that supports industry-standard equipment and probers. If you need parametric testing, contact Chroma for the Hyperion test shell. Wafer size can be set with the pull-down menu. As you change the size, the wafer graphic is updated. Notch or flat can be selected, but flats are only allowed below 200 millimeters, and notches are required above 200. The reticle size can be set, which will update the wafer graphic. The number of reticles that appear on the wafer will change as you alter reticle size or alter wafer size. The wafer clip defines testable reticles on the wafer edge based on clipping. Sometimes partial reticles are used in parametric test. This requires clip none. The FQA is used to define the edge of the wafer that production equipment can use to hold the wafer in place, and is usually a defective area. Using FQA adds an extra internal clipping radius to remove reticles that fall into this area. The wafer orientation defines the location of the notch or flat relative to the orientation of reticles, modules, and test structures. The wafer prober uses this information when loading the wafer onto the chuck. The wafer origin defines where the origin is located once you've selected a quadrant. The default is to put it at the corner of the quadrant. Here we're putting the origin at the center of the wafer. Wafer quadrant defines the direction of increasing coordinate value of the wafer and reticle for movement and data logging. Hyperion builds the reticle grid dead center in the middle of the wafer. However, that's not how all wafers are laid out. Some shift the grid. This results in the number of reticles at the edges being different than expected. By adding X or Y offset, the clipping will change the number of reticles to match how the wafer was actually laid out. The alignment reticle location defines which reticle the prober's auto-aligner will leave the chuck positioned at after wafer alignment. It is the reticle from which testing will start. We will move the reticle alignment to the topmost left reticle by finding its location in the coordinate axes. A reticle has a type. Multiple reticle types can be created. We need at least one. The graphic is the reticle type's representation. Reticle types can be named, have descriptions, and a unique color, which will become important once we begin selecting reticles to test. We need to create a reticle type which can be applied to reticles on the wafer. Click on the Add Reticle Type on the upper right side. We can click on Pick Reticle Color to get a color selection dialog. Different colors can be defined to each reticle type. This can facilitate visibility and contrast between multiple reticle types. We click on Select Reticles to get a dialog for selection. Locations can be selected by clicking individual locations on or off. This is where the reticle color becomes important. Locations can be selected also by rubber banding. Click and hold the mouse and then drag to select locations. Click and hold the mouse and then drag to select locations, ending by releasing the mouse. Once you've made an initial selection, rubber banding again will select an entirely new selection and delete all the prior selection. But if you hold the Shift key while rubber banding, new rubber band selections will be added to the prior selections. This is indicated by the selection being green while rubber banding. Similarly, you can hold down the Control key while rubber banding, and new rubber band selections will be removed from prior selections. This is indicated by the selection being red while rubber banding. Notice the whole time we've been graphically selecting and deselecting, a list of coordinates on the right have been updating as well. We can edit coordinate values in this table, and the wafer graphic will update. We can add locations by typing in the coordinates and hitting return. We can delete a location by deleting each of the coordinates. In all of this, we can also undo and redo selections along the way. Once we are satisfied with the selection, we click on Cut. Once we are satisfied, we can click on Accept, and that will update the selections to the main graph. And that will update selections to the main wafer display. Test plan definition. To create a test plan, we need to have a reticle type defined, like the blue one on the right side. We can go select reticles on the wafer to find reticle locations upon which to perform testing. Any selected reticle will execute its testing hierarchy located below the reticle type definition. Adding a module. Under the module square, there is an Add Module button. This opens the Add Module dialog. The first entry is the module name. Normally modules are named, and this name is often etched in metal on the wafer just above the module. It is also usually included in the documentation of the wafer test structures. The next field is the user group, which provides a naming system to optionally differentiate modules. For example, multiple modules of identical MOSFETs may be laid down for parametric tests, reliability tests, such as plasma damage, or other purposes. Setting the user group allows specific modules to be differentiated by these different purposes. The data taken on these modules will then be marked with the user group ID. The next field is the description for the module. Then the module's offset from the alignment module must be defined in microns. This is critical information for proper wafer movement to the module. Orientation defines the direction of the module. This is only for wafer probers which can accept alignment files specified by name or by data downloads over GPIB. This feature allows both horizontal and vertical scribe lane test structures to be automatically accessed within the same test plan. Alignment file names for each orientation must be provided. Switching between the two does require that the wafer be unloaded, reloaded, and realigned, as well as additional bond pad scrubs being suffered. So doing all vertical and then all horizontal modules or vice versa is strongly recommended. Pad size is currently only used for the UI, but will be used in the future for additional features. So if you can provide this value and specify it, you will be future-proofed for future revisions of Hyperion. Force serial forces execution to be performed serially, even if parallel testing has been enabled. This only applies to the Chroma 3530 and certain other third-party test equipment systems. Note that when you change the XY offset of the module, the yellow graphic mark will change location within the blue reticle square, indicating the module's relative location within the reticle square. Next is to add a device to the module. To do this, select the desired parent module and the Add Device button will be enabled. We select Add Device, which opens the Add Device dialog. On the left side of the open dialog are categories of devices. We will choose a 2-terminal resistor. Selecting this device type will change the right-hand side to show a resistor schematic, its parameters, and the module bond pads. The default name can and should be changed to match the device naming convention you use. There is again a user group which can be left blank if you do not need user groups. And then finally is the description. The schematic symbol of the device has text fields at each terminal for bond pad numbers at write. The connection of the device to the module bond pads is defined by entering a bond pad number into the corresponding terminal field. In this example, we connect them to pad 1 and pad 2. As soon as we do this, the module's graphic bond pads will turn blue to indicate they were connected. You can add additional device terminals to the same pads even if they are already blue. It is legal for a bond pad to share multiple device terminals, though there are sometimes implications and limitations for parallel testing. Hyperion will detect and analyze such situations before test execution begins. New device types can be created if those listed are not sufficient. The device types are defined by ASCII JSON files and can be created by the user. Algorithms. Next is adding algorithms to devices to define what measurements are to be performed and under what test conditions. We select the parent device upon which the algorithms are to be performed to enable Add Algorithm. Selecting Add Algorithm opens a dialog with a list of allowed algorithms for this device type. Selecting Resistance to Terminal causes the inputs, outputs, limits, and dependencies to be displayed at the right. We can change the input values. Defaults are provided by the algorithm coder, but the defaults can be changed to within the range of values defined. The link field allows output values from another algorithm to be fed into this algorithm. For example, you might perform an initial test to obtain a bias condition to be used for later algorithms. In the Outputs tab, we have the measured output variable names of the algorithm. The tag field allows the output variable name to be changed. In this example, we've changed the output value from resistance to R contact. In the output data, this will be the listed data name for this module, device, and algorithm result. The Limits tab define an output range for each variable, where values outside of which triggers a violation. An action will be triggered by a violation, including terminating a test plan, skipping the device, module, or reticle, dependent upon a certain number of violations to trigger the action. Execution order. The execution order of a test plan will follow the order seen in the test plan tree from top to bottom for serial execution. When parallel execution is supported by hardware and enabled, we'll have implied timing that cannot be guaranteed. Sometimes this is fine, other times this should not be allowed. This is the scenario when the Dependencies tab comes into play. To change or optimize parallel testing on the Chroma 3530. If certain tests must be executed before others, this is a dependency on the completion and execution order. If no such requirement exists, parallelization will execute as many algorithms not constrained by circuit topology as it can. Hyperion algorithm creation. Hyperion provides a programming interface in C++ for algorithm creation, though you won't need to know very much C++ to code your own algorithms. All structures, definitions, and interfaces to a Hyperion algorithms are entirely defined within the one algorithm source code file. There are no separate files required to manage or worry about. Let's start with a simple algorithm example, G-leak or gate leakage current. The includes define what base class and what instrument options are being used. The alg include is the standard base class for algorithms. There is also a rel-alg, which is a special reliability base class. The most common instrument to include is SMU, which provides DC measurement control. Others include CMU, FMU, PGU, and others. The alg start command defines the algorithm class definition. You don't need to know the gory details of the C++ behind this, because we've hidden that so that you can focus on making algorithms. The next commands define metadata details about the algorithm library that you are creating. You can create a library with only one algorithm, but more likely you'll want to create many and organize them appropriately. Looking at the Add Algorithm dialog, we can see a one-to-one correspondence between the listed algorithms and the C++ commands below. The name of the algorithm is defined by algname. The text description of the algorithm is defined by algdescription. You can create organizing groups and subgroups which define the hierarchy you see in the Add Algorithm dialog. Alggroup defines the top tree node. Algsubgroup is a descriptor that you can sort on within the group. And finally, you can add a version number with algversion. Your library name is defined by alglibrary. You'll notice that other libraries may intersperse related algorithms that have the same group and subgroup labels. Here's how the GUI for gate leakage inputs and outputs are defined. In this command, you'll see a one-to-one which also defines the variables used within the algorithm to access that same data that will contain the input value. The next value is the default value for that input. Next are the minimum and maximum values for the input. The next argument is the tag variable, which is the default value for the input link field if specified. The last value is the description of the variable. You can also define integer and string inputs by using the alginputInteger and alginputString commands. The next two input types are more unique. First, we have an enumerated input. This gets displayed in the GUI as a combo box or drop-down menu. We are using this type for integration time. The first argument is the variable in C++. The next argument is the default value. Next is the list of enumerated values that are allowed. And finally, the description of the enumerated variable. The next type is a Boolean, which is displayed as a checkbox. The first argument is the variable in C++. The second argument is the default value. Following that is the description of the variable. Next are output field definitions. For gate leakage, we only have the scalar double value of igate, declared by algoutputDouble. The first argument is the variable. The second argument is the physical unit as a string. The next argument is the tag field, which is empty, but is used to rename variables for linking or output formatting. And finally, the argument description text. Another important type of output field, not used by gleak, but worth mentioning, is the double array output. In many other test systems, you have to deal with vector data and file management for that vector data on your own without any standards or APIs. Hyperion supports vector data as a full first-class data type, like scalar result data. The selected data output formatters will handle vector data automatically just like scalar data. There are two types, alg output double array and alg output double array real-time. Both work the same, and the latter is a superset of the former. The difference is that real-time data is published for runtime point-by-point display to the execution GUI. Using real-time can affect performance, but its target use is for reliability algorithms which run for a long period of time, or for just one or two algorithms to indicate data correctness. The first field is the variable name that you add data to in the algorithm. The vector output data is implemented as a subclass of C++ STL standard vector double. You can use append of value instead of the standard pushback value, for instance. The next argument is the physical unit as a string, and then the tag variable, and then finally the variable description. The next command is alg device type, which defines which devices can use this algorithm. This helps both usability and organization of the test plan. For example, adding a transistor test to a resistor doesn't make any sense. However, closely related device types can be allowed to use an algorithm, as in the case of MOSFET and MOSCAP, which can both use the G-League algorithm. Resources. Next, we declare variables to define the required test resources. In this case, we need a single SMU channel, which is called gate SMU. This resource must have its connection to the device under test defined by the request SMU high connect and request SMU low connect. Depending on which vendor's SMU you were using, this may seem confusing. Simply remember that any Keysight SMU always uses a global SMU low terminal called the ground unit. For Keysight instruments, that is what will be connected to SMU low. For Keithley SMUs, there are both high and low connections explicitly separate, so this will already be intuitive. Next is the device terminal connection. If you have only one device type, there is simply the string of the terminals of that device type. If you have multiple device types, you need to use the structure you see here to tell the algorithm which device types pins are used for which connection. Next, the MOSFET device type has additional and optional terminals. The minimum MOSFET has drain, gate, and source, but optionally can have additional terminals defined. We have all of them connected to the drain terminal here. Constants and variables. You can define any constants or variables required here. They have scope over all execution functions. This means code can access these variables in algSetup, algrun, alganalyze, and algfinish functions. If you want to pass data between different execution functions that are not inputs or outputs, you will need to declare a variable to do that. You can pass scalars like the polarity example here, or you can pass vectors, usually in standard vector double format. The scope of all input and output variables are also over all execution methods. algSetup is the first execution function. You should use algSetup for setting up measurement resources, variables, etc., and do any initial calculations based on the input values that will be used in the setup. In this example, we calculate a new device polarity if the device is a MOSFET based on the MOSFET's device type channel variable. Next, ranging and compliance for the gate SMU are defined, and then commands are executed. We use execute because it is essential for coordinating parallel execution and speed up for both parallel and serial code execution. algrun. algrun is where the core of algorithm interaction with test resources should occur. In this case, we enable the gate SMU, force the stimulus value, define a delay, and then define the measurement with a result variable, current command. Next, the result is tested in an if-then statement to check if the gate SMU went into compliance during measurement. If it did, we print a text message to the runtime console indicating this. Then the iGate output value is set to an in-band coded error dummy value of -2.0 E30. Otherwise, if there is no compliance, the iGate value is set to the measured current from the current command variable. Alg-analyze. Alg-analyze is not used in GLeak. But if you had measured vector data from a sweep instead, and then if you wanted a linear regression, you would write vector data in algrun and then perform regression in code in alg-analyze, assigning regression output variables. Alg-finish. Alg-finish is where any shutdown of test resources should be done. In this case, we set the gate SMU to 0 volts. We also write the iGate value to the runtime console.